Hi class, welcome to the next section, chapter 4.1, the first section for chapter 4. So chapter 4 is all about, I guess you could say, shortcuts for finding derivatives. So previously we've been finding derivatives by using limits and counting the, using the difference quotient as h goes to 0. So what we'll notice is that we can find some shortcut rules for finding derivatives for certain functions and certain combinations of functions. So this is our first section on that, derivatives of polynomial functions. We're going to go through a little bit of review that I'm sure a lot of you probably haven't seen before that will make some of the topics in this section a little bit easier before we get into the polynomial portion of it. Finding derivatives of polynomials is the easiest derivative to find, right? So that's how we start with the derivative of polynomial functions. You probably feel like polynomials are like your worst function to deal with because there's so much that goes into it when you're looking at the zeros and the end behavior and all the other things that come with it. We spend a lot of time analyzing these types of functions. So it's nice that the derivative of polynomials are really, really easy to calculate. Okay. So we're going to take a step backwards and kind of build our way up to that progression of finding the derivative for a polynomial function. Okay, so we're going to start with what's called Pascal's triangle. So I'm not going to go super deep into Pascal's triangle. I do in my pre-calc class. So if you want to see a little bit more on this topic, then I would suggest you go to my pre-calc section and look at that there. If you've seen it before, then this will be a breeze for you. So Pascal's triangle is a way to find coefficients for any binomial expansion. So remember, a binomial is two terms, okay? So any two-termed polynomial raised to a power can be found through Pascal's triangle. It's a really, really useful tool, and we're going to use it to figure out how to find a generalized formula for the derivative of a polynomial. So Pascal's triangle is useful because it's used more than just polynomials. It's also used in probability theory, in statistics. It's kind of used everywhere, right? So it's helpful for finding combinations and permutations, which we're not going to go over now. But again, if you're interested in that kind of stuff, you could go to to my pre-calc stuff and look at it there. Okay. So Pascal's triangle is really, really easy to create, and it's very patternistic. So it's really easy to find the pattern for it, and we use the pattern of Pascal's triangle to talk about the pattern of powers of binomial expansions for polynomials. Okay, so we go one row at a time. So we start with 1, okay, and then when we go to the next row, we're going to take the entries above to fill in the entries for the next row. So we go one row at a time. If there's a 0, so we're taking the two values above to the left and to the right. If there's nothing on one of those sides, then we count it as 0, and so we would have 0 plus whatever that value is. Okay, so for the nth n equals 0 row, we just start with 1. For n equals 1, I'm sorry, so we're going 0 and then 1. So this is not the first. It is the first, but it's not. We count it as 0 first. And then the first row. So here, this is going to be, there's a 0 on either side of these this one that you don't see. So when we add 0 and 1, we get a 1. And here, 1 plus the other 0 that's invisible on the right side would add to a 1. So that's how we get the 1 here. So then for the next row, n equals 2, we're going to have a 1. And then the middle value will be 1 plus 1. So I'll have a 2 in the middle. And then a 1 on the end. Okay, because there's nothing above it on the left. Plus the 1 gives me just the 1. 1 plus 1 will give me 2. And then this 1 plus the 0 that's on the right, that's not visible. There's nothing there, right? Will give me another 1. For n equals 3, it'll be the same thing. It'll start with a 1. And then it will be 3, and then it'll be another 3, and then another 1. For the next row, same deal. It starts with a 1, 4, 6, 4, 1. Okay, see the pattern? And then for 5, we'll have a 1, 5, 10, 10, 5, 1. So if you notice, along the left side, the outermost left side, it's always a 1. If you go one more diagonal in, it goes 1, 2, 3, 4, 5. Obviously, this next one will be 6. If you go one more row, 1, 3, 6, 10, it's counting by 2, and then 3, and then 4. So this next value will be 15. So you can see here, the difference is increasing by 1, 2, 3, 4, 5. Okay, here you have a difference of 3, and then 6, and then I'm not really sure what the pattern would be. We'd have to do more lines. And then it's reflected on the other side. It's symmetric. It's all ones. 1, 2, 3, 4, 5. It'll be 6, 7, 8, 9, 10. 1, 3, 6, 10, 15, 21, 28, etc. Right? I'm increasing by one more. Here again, we can't really see what the pattern is, but it doesn't matter because if I have half, I could fill in the other half. Right? So if I go 6, it'll be the same thing. 1, this will be a 6. This will be 15, 20, 15, 6, 1. And it continues forever and ever like that. Okay, so that's Pascal's triangle. Now, I'm going to go over some stuff with you now, and I'm sure it'll be repeated in, in a paragraph somewhere. But notice that these correspond to the powers of a binomial expansion. Anything to the 0 power is always 1. If I have, let's say, x plus 1 to the first power, that's x plus 1. If I have x plus 1 squared, that's x squared 2x plus 1. If I have x plus 1 cubed, that's x cubed plus 3x squared, or cubed plus 3x squared plus 1. So these are the coefficients for a binomial expansion. Okay, so n is the degree of our binomial expansion, and the values in the rows are the coefficients for our binomial expansion. Okay, so again, if I had x plus 1, right, 1 for x and 1 for the value 1 here, to the 0 power, that's 1. Okay, x plus 1 to the first power, 1 plus 1. The coefficient here is 1, coefficient here is 1. Right? Coefficient, coefficient. X plus 1 squared, 1, 2, 1. Okay, 1, 2, 1. X plus 1 cubed, 1, 3, 3, 1. X plus 1 to the fourth, 1, 4, 6, 4, 1. And so forth, right? It's very, very easy to find these expansions. You don't have to take x plus 1 and multiply it times itself 4 times. You can just do 4 rows of Pascal's triangle, which are really, really easy to find, right? It's a really patternistic. Okay. All right. Let's go back here. So now I can use this not just for x plus 1. But what if I had x plus a, right? So when I say a, maybe this is x plus 3 to the 4th power, or x plus y squared to the 5th power, or even if this is to a power, right? Let's say that this is x to the 3x 4th plus 2x, or 2 plus 2, okay? I can do the same expansion using Pascal's triangle. And that's what we're going to talk about today, is how to use this triangle to find any sort of expansion for a binomial. So, let's see here. Okay, so again, the way that this works, when it's not just x plus 1, when it's any generic thing plus any generic thing, this can even be a minus, right? We would just consider this a as a negative value. Then what happens is that the a term is going to multiply across this x term, right? Increasing in power starting from 0. So I'll have an a0 term in front. A to the 0 is 1, so it's not going to affect what happens in front. Then I'll have the same thing going on, 4x cubed, but times an a to the first power. And then I will have this, same exact coefficient, same 6, same x squared, but I will have an a to the 3rd power. Or 0, 1, a squared. This will have an a cubed term, and this will be a to the 4th power. Okay, so the a term starts from 0 and increases in power. The x term starts at its highest, 4, and decreases in power. It goes 4, 3, 2, 1, 0 for the first term. That's what the first term is doing. The second term is going 0 power, a to the first, a squared, a cubed, a 4th. Okay, when I have something that's not a 1. Here, 1 to any power is just 1. That's why you don't see it here. So when I have the two terms here, whatever is in front is decreasing in power. Whatever is in back is increasing in power. And I still have the coefficients from Pascal's triangle involved. Okay. So for instance, x plus 2 squared is going to be x squared times 2 to the 0 power. Okay. With a coefficient of 1 from Pascal's triangle. I'm going to have 2. So remember, x plus the square term is 1, 2, 1. So I have a 1. I have my 2 from Pascal's triangle. My x is going to be decreasing in power. So it's going to go x squared, x to the 0. My 2 is going to go 0. I have my x1. So then I have my 2 to the first power. Okay. So here, so first things are the coefficients. Next is the powers of the x's. And then last, I will have the powers of whatever this last term is, right? So then for my next one, I have a coefficient of 1 from Pascal's triangle. My x's are going down, x squared, x1, x0. And then the values from here, 2, 0, 2, 1, there will be a 2 squared here. And now I just simplify, right? This is x squared, 2 to the 0 is nothing. This is 2 times 2, so 4x. And this is going to be 4. So x squared plus 4x plus 4. And we should know this because if we factor this, we know it's x plus 2 squared. Okay, that's an easy one to check. So if I go higher and I go x plus 2 cubed, I don't really want to take this and multiply it times another x plus 2. I'll just follow the pattern. So I'm going to have 1, 3, 3, 1. That will be present. My x's are going to go x cubed, x squared, x, and then none. And my 2's are going to go 2 to the 0, 2 to the 1, 2 squared, 2 cubed. Okay. So again, 1, x cubed, 2 to the 0. Next, I will have a 3 from Pascal's triangle, x squared, and then 2 will go up to 2 to the first. Okay. The next term will be another 3 from Pascal's triangle. And then my x will go down in power to x1, and then my 2 will go up in power to a 2 squared. And then last, my x's go to 0. The coefficient from Pascal's is 1 and 2 cubed, right? So if we look at, just to quickly go back for 3, right? 1, 3, 3, 1. Let's get over here. Okay. Coefficients are 1, 3, 3, 1. Okay. My x's go x cubed, x squared, x to the 0. My 2's from this term here, from the a position, to 0, 2 to 1, 2 to squared, 2 cubed, right? It's a pattern. Simplify all these. I have just x squared. This is 3 times 2. This is 3 times 4. And then this is just 2 cubed. Okay. Now, if I change it up and I do something a little bit crazier, it doesn't matter. It's the same thing. Everything in this term is going to be what's happening to my x cubed. So I'll have a 2x cubed. I'll have a 2x squared. I'll have a 2x plane and a 2x to the 0. I will still have a 1, 3, 3, 1. And for what's happening at the end, instead of 2, 0, 1, 2, 3, it'll be 3 to the y to the 0 power. 3y to the first power. 3y squared. 3y cubed. And it's not just 3y, but it's negative 3y. So all the odd ones, like this term, where it's a 1, and this one where it's a cube, will have a negative sign, and all the even-powered ones will be positives. Okay? So, coefficient of 1 from Pascal's, 2x cubed, negative 3y to the 0. Okay? Plus a 3 from Pascal's, 2x squared, negative 3y from 0, first power. Okay. Then I'm going to have another 3 from Pascal's. 2x is going down, 3, 2, so it'll be just the first power. Negative 3y is 0, 1, it'll be a square. And then for the last one, everything is gone. I have a 1 from Pascal's, 2x to the 0, okay, and negative 3y cubed. So I just simplify it. I know it looks like a lot, but it's actually really easy. This is 1, so this is just 2x cubed, so that'll be 8x cubed. Okay. This is 2 times 2 is 4. and then 3 times negative 3. So negative 36x squared y. Okay. Here I'll have positive 9 times 3 is 27, and double that is 54 xy squared. Okay. This one is going to go away, and I'll have a negative 3y cubed, so that'll be negative 27y cubed. Which is much, much easier again than taking this and multiplying it times itself 3 times. This is really, really obvious that it's an easier version when you're doing something like this to the 4th power or this to the 5th power, because it's very easy to find the coefficients using Pascal's triangle and using this repetitive patternistic sort of approach to it, rather than chugging it out and trying to just do this by force, right? Doing this times itself 5 times. It's kind of a lot. So we can say that in general, x plus a to the n has this form, right? C naught x to the n, C1 x to the n minus 1. So if you notice, the x ends, the x is decreasing power, n minus 1, n minus 2, all the way down to square x and not present at all. The a value is increasing power. There's not one present in the first term, right, because of Pascal's triangle. Then we have a 1, and then a square, and then a cube, and so forth, until we have 2 less than n, 1 less than n, up to n. And these C naughts, C0, C1, C2, all the way through, these are just the coefficients based on Pascal's triangle. Okay. Now there's a way to calculate these explicitly, which I'm not going to go over in this course because it doesn't really matter here. You can, if you're interested in this, if this is interesting to you, again, go to my pre-calc session and you can look at that, and we go a little bit deeper in it than we are here. Okay. So again, each of these CIs come from Pascal's triangle. They're the coefficients based on the triangle. So let's just do a second example, right? Another example. Or actually, let's find the derivative for f of x equals x to the n. So this is a general power function, right? If you think about what a polynomial is, it's really just a bunch of these being added together. We know from our properties of limits, we could take the limit as h goes to 0 of each of these independently, right? Which is kind of what we're going to do later on. So we're going to find the derivative of a general power function. So we're going to use the limit definition because that's all that we have at the moment. So the derivative of f, is the limit as h goes to 0 of the difference quotient of that function, right? So we're going to plug in x plus h to the n power. Do you see why it's important for us to know how to expand this if we're doing it to the nth power? Minus f of x. Okay. So I'm going to take the limit as h goes to 0, have x plus h to the n, okay, which we have a generalized form for here. I would just be replacing all of my a's with h's basically, right? And I'm going to subtract from that x to the n and divide by h. So I don't know why I wrote this twice. Sorry guys, probably so that we could see it. Anyways. Okay, so I have my x plus h to the n expanded here, minus my x to the n. So here you can see we have x to the n. The coefficient for the first one is 1, right? The coefficient for the next one would be going to be n, because remember what happens in the triangle. Let's go over it one more time. The second value is always your row number, right? So n to the 5th, right? This binomial to the 5th power, that value is 5. So I can kind of shortcut my way through here a little bit. Okay. So the first coefficient is 1. The next one is n, whatever that power is, right? And that means since it's symmetric, for the last one, when you go h to the n, that coefficient is 1. And then 1n is also n. So that's why I have C3 here, but then it's 1, whatever the power is. And then this one we'd have to find using some other means, binomial expansion, which we're not going into. Okay, but this is the generalized form for that x plus h to the n minus my x to the n. Now notice what happens is that this first term, x to the n, subtracts from my x to the n function. Okay. So now what I have has an h everywhere. An h squared, an h cubed, an h to the fourth, all the way up to h to the n. So every term now has an h in it, so I can divide everything by h. Okay. So this had only one h, so it's nx n minus 1. Everything else still has an h because the powers of h were more than 1, so when it canceled out with h, there's still at least 1 left. Now, this is a polynomial, right? It's x to the n minus 1, x to the n minus 2. So like, let's say this was x5, x4, x3, x. It's still a polynomial. So as h goes to 0, this disappears, everything disappears except for the term that doesn't have an h in it. Okay. So the derivative of f of x equals x to the n, any generalized power function, has a derivative of n times x to the n minus 1. So that's the generalized form. That's the formula now that we can use in this class wherever and ever. Okay. So the way that this works is whatever power was here comes down and multiplies, and the value that was there decreases by 1. Okay. So let's do an example. I want to find the derivative of f of x, 10 to the x cubed minus 3x squared plus 10x minus 50. This is several power functions being added and subtracted together. So I can take the limit of each one independently, or the derivative of each one independently, because the derivative is just a limit. So all the rules I had for limits apply for my rules for derivatives. Okay. So we're going to start with the limit definition, which means that I'm going to have this 10x cubed, x plus h to the third. So everywhere I see x, I'm going to plug in x plus h. Okay. And I'm going to subtract from that my original function over h. All right. So I'm just doing to my function the limit definition as h goes to 0. So this is a lot of expansions to have to do, right? If we didn't have this rule already. So here I'm going to distribute this negative sign. So this turns into negative 10. This turns into a positive 3x squared. So you can see I distribute this negative sign and I grouped everything together. So this negative 50 and this positive 50 are together. This 10x plus h cubed is now grouped with this negative 10x cubed. This 10x plus h is grouped with this now negative 10x. So I distribute the negative sign and I grouped the terms together, right? So the cube with the cube, the square with the square, and so forth and so forth. So now what I can do is I can separate this into several difference quotients. Okay. I got the limit of one difference quotient plus another difference quotient plus another, right? So I'm separating them into their pieces. Still one single function, but now I can take the limit of each one independently. Okay. And that's what I really wanted to get out, is that I can take this one single function and apply my rules of limits so that I have several derivatives being added together, right? So I separated the cube and I put it with the cube and I separated in the term and distributed my limit. So now I have the limit of 10x cubed, right? I have the derivative of negative 3x squared. I have the derivative of plus 10x. I have the derivative of negative 50. So applying these rules, okay, again, remember I said we like to use this prime notation, but we'll also use this Leibniz notation. So I have 10x cubed, because this limit is the same as 10x cubed. This is the same as the derivative of 10x cubed. This is the same as the derivative of negative 3x squared, of 10x, and of negative 50. So I can really just apply these rules instead of doing this binomial expansion and canceling out the h's and all that kind of stuff, right? So remember what happens. This 3 comes down, okay? Actually, before we do that, I think what we're going to do is we're going to pull out the constants, right? Because, again, whatever we can do for limits, we can do for derivatives because the derivative is a limit. So here, you see I have a constant of 10 and 10. I could pull this out. I could pull this out as a constant and then just take the limit of the difference quotient of x cubed, right? So I can do the same thing with derivatives. So I I guess I'm just going to go for it. So we're going to have 3 times 10 is 30. The 3 is going to decrease by 1. 2 times negative 3 is 6. This 2 is going to decrease by 1. Okay. There is an invisible 1 here, so this turns into 10, and then the 1 decreases by 1, so it turns into a 0, so this is just 10. And this is negative 50 times x to the 0 power, so 0 times negative 50 is 0, and 0 times, doesn't matter what happens to the x, it's still 0. So the derivative of 10x cubed minus 3x squared plus 10x minus 50 is 30x squared minus 6x plus 10. So again, 3 times 10 is my 30. The power decreases by 1, so it's 2. 2 times negative 3 is negative 6. This power of 2 decreases by 1, so it's just a 1. The invisible 1 here multiplies times 10, so it turns into 10. And the 1 drops down to a 0. X to the 0 is just 1, so that's a 10. And this 50 drops off. Okay. So if my function is 10x cubed minus 3x squared plus 10x minus 50, then the derivative is 30x squared minus 6x plus 10. So again, let's just kind of rehash what this is. This function tells me the slope of the tangent line at any point for this function. This function, this derivative function, tells me the rate of change instantaneously at any point for this function. Okay. So this gives us what's called the power rule, right? If my function is a power function, x to the n, then the derivative of a power function is n x to the n minus 1 power. Okay. So now let's talk about properties of the derivative. So these are really just a refresher of the properties of limits, because again, the derivative is a limit. So all the rules that we have for limits apply to derivatives. So these properties of derivatives are really just properties of limits. Okay, so let f of x and g of x be functions, and let c be a real value. So c is a scalar. If the derivative of f plus or minus g is going to be equal to the derivative of f plus or minus the derivative of g, right? So just like for limits, if I had the limit of two functions being added together, then I can take the limit of the two functions separately. So it's the same thing because derivative is a limit. So just like we did previously here, I took the derivative of this entire function, but if I look at this function as several functions being added together, I took the derivative of them separately, right? So same thing. If my function is two functions being added or subtracted, I can take their derivatives separately and add or subtract them appropriately. Right? So using our prime notation, it's the same thing. Okay. If my function is a constant times a function, then just like with limits, I can pull that constant out and then just take the derivative of the function. So as I was saying before, which we did not do, I could have just looked at this as x cubed 10 times the derivative of x cubed, and I would have had 3 times x squared, and then multiply that times 10, and I still get 30x squared. So I can always pull out this constant value and just focus on the function itself. Okay, or in prime notation, it's c f prime of x. The derivative of a standard x function, just a line, is going to be 1, right? The coefficient is 1, the power is 1, so when the 1 comes down, the power of 1 that was here goes down by 1, turns into 0, and that turns into 1 times 1. So the derivative of x is just the constant 1, which is why we saw 10x here turn into just a 10, because x goes to 1, and we have 10 times that derivative. The derivative of a constant function, just like here, will go to 0. Okay. So these are the 4 main ones. So let's look at an example. So find the derivative for the following functions. Here we have 5x to the 9th. This is, very straightforward. Depending on what rules I want to use, I can separate the 5. This 9 is coming down to multiply across the 5. The 9 decreases by 8. 9 times 5 is 45. And the 8 stays, right? So the 8 dropped down by 1, and the 9 comes down to multiply times whatever constant or coefficient is in front already. Okay. Here, same thing, we have 4x, the power here is 1. Okay, so the 1 comes and multiplies times the 4, and it drops down to 0, so you get 4 times 1, just 4. Right? So I always think about it as, if we have something times x, the x just goes away. Okay. If we have a constant, the whole constant just disappears. Anything else, we apply these rules. Okay. Here, 6x to the negative third, it doesn't matter. It's the same thing. It doesn't matter if it's negative or not. The negative 3 comes down, and this decreases by 1. So we get negative 18 times x to the negative 4. Okay. So the negative 3 comes down and multiply. Negative 3 decreases by 1. Negative 18 x to the negative 4. Here we have a constant. We know constants go to 0. Okay. So looking at it in terms of the rules, okay, the 1 comes down, x goes to 0. Okay, or I'm sorry, you can think of 6 as 6 times x to the 0. So the 0 comes down to multiply times the 6. X goes to negative 1, but it doesn't matter because it's multiplied by 0. So the whole thing goes to 0. Okay. Here we have f of x is the cubed root of x squared. Now you might say, oh, Professor Limbs, this isn't a power function. But it is. You take this cubed root, right, this nth root, and you turn it into a power. Okay. So this is the same thing as x to the 2/3 power. So now when we apply our rules, the 2/3 drops down and multiplies times the x, and then we decrease 2/3 by 1. Okay, so I got 2/3 x to the 2/3 minus 1 power, or to simplify, because that's not what we want as an answer, 2/3 minus 1 is negative 1/3. So this is 2/3 x to the negative 1/3, which, to be honest with you, I am 100% fine with you leaving this as an answer. In fact, I would rather you leave it like this as an answer. Okay, this is my preferred form of an answer. It's weird because in every class up to this class, you're told not to leave negative exponents, right? They always say apply these rules. To be honest, from calculus and above, we don't want to see these in any other way. We would much rather see it like this because this is easy to work with. All the other ways where you put it in the denominator, and then if you put this as a cubed root of x on the denominator, that's fine, but it's preferable to keep it like this, because if I have to do any other work on this, this is the method that I would prefer to use. Okay, so if I did have to bring it down all the way, I guess this is an okay answer. Really, if you're gonna go further than this, take it all the way down. Okay, this is where you should go. So either keep it in this form or take it all the way here. Okay, preferably here. This is my preference. Okay. So again, any of the last three are acceptable. Although this I feel is you being proactive, but also lazy at the same time. Because if you're gonna simplify it further than this, then take it as far as you can. Okay, but I will accept any three of these as an answer. But again, this is number 1. This would be number 2. This would be my least favorite answer. Okay, do not keep it like this. I'm taking points off for something like this all day. Okay, don't leave me with more math to do. Right, this doesn't leave me with math. This is a nice compact form. Okay, so let's do another example. Now we're going to use the derivative as a function to answer some questions. So we've been answering questions using derivatives already, finding tangent lines and things like that. But it took a long time because we had to use the limit definition. Now it's a lot faster because we have a generalized formula for that. So we want to find the line that's orthogonal. Orthogonal is the same thing as perpendicular to the parabola y equals 2x squared minus 3x plus 5 at the point negative 1, 10. Now let's think about this. If I want my line to form a right angle with a curve, that's kind of hard to do because the curve is always changing, right? So what we need to do first is we need to find the equation of the tangent line and then find the line that is perpendicular to the tangent line at the point that's given to us, because then it'll be perpendicular to our curve, right? So we need to find y prime to find the tangent line, and then we need to find the perpendicular line to the tangent line at that point. So my derivative, if this is y, is going to be what? What do you think? So maybe pause this video, do it on your own, and then play it and see what you get. Okay, hopefully you paused it and you just came back. So you should get 4x, and this should just be -3. Okay, so this is not your tangent line. This is just the derivative of this function. This is the equation that will give you the slope of the tangent line at any point. Okay, so we don't need to actually find the tangent line. We just need the slope of the tangent line, right? Because the perpendicular has a special relationship with the slope of the tangent line. So I just need the slope of the tangent line. So I'm going to plug in -1 to my tangent line. So I'll have 4 times -1 minus 3. So I'm going to put this all together. I'll have a -7. So -7 is the rate that my function is changing at the point x equals -1. Okay, so if I take the negative reciprocal of this, that's going to be the slope of my orthogonal line, my perpendicular line. So that means that the orthogonal line has a slope of m equals 1/7, and it satisfies the point -1, 10. So all I got to do is put those two things together into y equals mx plus b. So remember that this is y equals m and x, and I'm solving for b, right? So I'm going to plug everything in. I can play with my fractions, or I can clear out my denominators, which is what I prefer to do. So this will turn into 70, this will be a -1, and this will be 7b, okay? And then when I solve for that, I will get 71/7. So that means that my orthogonal line has the equation 17x plus 71/7, and this line is going to be orthogonal to this curve at that point. Okay, so let's throw that on Desmos real quick, just so that we can see that. Okay, so we have my function 2x squared minus 3x plus 5. If I graph the tangent line, which we didn't calculate, but I do have here for us, right? Slope of -7x ends up being 3 as the y-intercept. This is the orthogonal line. So if I take this away, you can see that it does pretty much form, or not pretty much, it does, we calculated it, forms a right angle here, only specifically at that point. Okay. Right at that point it forms a right angle. Right. And now if you wanted to just kind of look at this as my function, and then we can have f prime of x as well. Okay, so this was my derivative function. Okay. And so we know that at -1, it should have an output of -7. Here we go. Okay. Right. So it all makes sense for us here. Let's look at another example. So suppose that we have a curve, y equals x to the 4th plus ax cubed plus bx squared plus cx plus d, and that this curve has a tangent line when x equals 0. And that the equation of the tangent line at x equals 0 is y equals 2x plus 1. And that when x equals 1, we have another tangent line of y equals -x squared plus 2. We want to find the values of a, b, c, and d. So we have this 4th degree polynomial. Okay. We know the equation of the tangent line when x is 0, and we know the equation of the tangent line when x is 1. So that means that when x is 0, the slope of the tangent line is 2. So the derivative of this function equals 2 when x is 0. The derivative of this function equals -3 when x is 1. Because remember, the tangent line is related to the derivative, and that the derivative tells us the slope of the tangent line at whatever given point. Okay. So first and foremost, we got to find the derivative of this function, right? So again, we know that our polynomial has points in common with its tangent lines at x equals 0 and x equals 1. So not only do I need to find the derivative, okay, but I know the slope at certain points, but if I plug in 0 to this equation, backwards, okay, if I plug in 0 to this equation, then it should give me the same value out as when I plug in 0 to the tangent line, okay. When I plug in 1 into this equation, I should get the same value as when I plug in 1 to the tangent line, because that's the points that they share in common, right? So that's what we're going to start with, rather than taking the derivative. We could go either way. We're going to have to do both, to be honest with you. So at x equals 0, my equation, when I 0, 0, 0, 0, I'm sorry, this is for the tangent line. When I plug in 0 to the tangent line, I get out 1. Okay, so 0, 1 is the point. So that means when I plug in 0 to y, everything has to go to 0, and all I'm left with is d, which means that d has to be 1 as well, right? When I plug in 1 to my tangent line, I get out -3 plus 2, or 1, -1. So that's another point I have here. So if I plug in 1, I should get out -1 for my equation. So plugging in 0, 1 tells me that d is 1, right? So when I plug in 0, everything goes away. I'm left with d, which has to equal 1, because when I plug in 0 to my tangent line, I get out 1, and they have a shared point only at x equals 0. Okay, I can't do that yet for 1, -1, because there's still 3 unknowns left. So if I plug in 1 here, I'm going to get a value out. I'm not going to have any information, so I'm not going to use this 1, -1 just yet. Okay. So what I started off with was telling us that when I plug in 0 to the derivative, I should get out 2 from my derivative, because the tangent line, this derivative tells me the slope of the tangent line at a certain point. So that's what we're going to do now. We know that the slope of the tangent line at these points, because I have my tangent lines, right? So my derivative of y is 4x cubed, 3ax squared, 2bx. This is just c, and d goes away. Okay, so now that I have the derivative, I can plug in 0 as well, and I know that I should get out a slope of 2, which is nice, because notice when I plug in 0 here, everything drops off, and I get c equals 2. So using this point 0 on the tangent line has helped me twice, right? Like right away I found d, because I know that if I plug in 0 to this and 0 to this, I get the same point. Okay, I know that plugging in 0 to the derivative will give me out a value of 2, which is the slope of the tangent line, because the derivative tells me the slope of the tangent line. So using this point and the derivative is nice. It tells me that c is 2. So now I have c and d. All I need is a and b, and I still have one point I haven't used yet. I haven't used this point 1, -1, and I haven't used the point x equals 1 and a slope of -3 with this line yet either. So using those two values, using the second tangent line and point with my equation and with my tangent line, I can figure out what a and b are. Okay, so that's what we're going to do now. We're going to use the point 1, -1 since we haven't used it yet. So when I plug in 1 to my value y, okay, 1 to the 4th is 1, x 1 cubed is just 1, so that's a, 1 squared is 1, so that's b. I know c is 2, and I know d is 1. So I have all this equal to 1, so when I simplify, that turns to a plus b is -5, right? So the a and b stay, everything else moves over, right? So this turns into a -2, a -3, and another -2. So I have this equation, okay? This in and of itself, I can't solve for a or b yet, okay? But I can use x equals 1, the derivative, and the fact that I should get out -3 for my derivative when I plug in 1, okay? So I'm going to use 1 -3 with the derivative, when I plug in 1 to the derivative, which was here, okay, 1 cubed is 1 times 4. This will just give me the 3a, and this will give me the 3b, and I know already that c is 2. So now when I solve this, I'll get another equation for a and b, right? I'll subtract 4, subtract 2, and now I have a plus b is negative 5. 3a plus 2b is negative 9, so that's a system of equations that I can then solve, okay? So I can do this by saying, hey, let's, a is negative b minus 5. Solve any way that you know. If you took pre-cal with me, then this should be a breeze. We studied systems of equations like crazy. So there's lots and lots of ways to solve this. You can use substitution, you can use matrices, you can use inverses, you can use all kinds of things depending on what you're familiar with. Or you can just use the elimination method. It doesn't really matter. Okay, for instance, if I subtract these two out, I'll have just b equals negative 6, and I can plug that back in here, and I get a equals 1. It doesn't matter. I'm not going to show the work for this because you should 100% know how to solve one of these at this point. Okay, but now I have a, I have b, I have c, and I have d. So I'm going to plug it in. This is the equation that I have for